Calculus is all about slopes, or gradients. We've already done a lot of work with gradients when we looked at straight lines. Now we're going to use calculus to find the slope at any point on much more complicated graphs. I'm going to use GeoGebra so that you can see what we're doing with calculus before we actually get into doing problems with it. Here we have an interesting function graphed, and I want to find the gradient at any point on the graph. But first, what do we mean by the gradient? We're good at talking about and finding the gradient of a straight line, but how do we find the gradient of a curve? Well, we just draw the tangent to the curve, and the tangent, after all, is a straight line, and therefore we can find its gradient. So if we talk about the gradient of a curve, we really mean the gradient of the tangent to the curve. Let's have a look at the tangent at the different points along the curve. The tangent is this red line. So there we saw all the tangents over that range of x. And as you could see, their gradients changed a huge amount as they were going around the curve. So this could be a bit of a problem. But for now, let's assume we've solved that problem, which we will with calculus, and just for now move on. So now suppose that I want to find the equation of the tangent when x equals 1. How do I do that? Well, first I have to find the actual point on the curve that corresponds to this x equals 1. How do I do that? Well, you've done this before. You substitute x equals 1 into the equation for the curve. And if we did that with this curve, I haven't shown you the equation, but I've got it. If we did that, we would find that y equals -2. So here is our point that we want to draw the tangent at. So now we draw the tangent there. Now we use our knowledge of straight lines to find the equation of this tangent. Wait a minute, aren't we missing something? Sure, we've got one of the points the line passes through, 1, -2. But it would be nice to know the gradient, wouldn't it? If we want to find the equation of the line. Then we could use the second of our straight line equations here and quickly find the equation of the tangent. This is the form of the straight line that you use when you're given one point and the gradient. But we don't know the gradient. Well, we could work it out using rise over run. You're good at that. But it is slow. There is a quick way. And that quick way is with calculus. Calculus has some flash words for talking about the gradient. If we have a function such as this cubic I've got here, then we differentiate it. That will give us the derivative, which gives us the gradient. You will get a lot of practice doing this in class, but for now let's assume you can do it. So you have the gradient, you know the point, and you can therefore find the equation of the tangent. In just a few lines. It is very quick, I promise you, once you know how to differentiate. Then we can even go a step further. Remember that special relationship between tangents and normals, or between their gradients? If you multiply their gradients together, you get -1. So if you know the gradient of the tangent, you can very quickly find the gradient of the normal. And how have you found the gradient of the tangent? Yeah, you've got it by differentiating. Okay, so as well as finding the tangent at the point, you could find the normal at the point. just using the same formula as you used for the tangent, but this time with a different value for m, the gradient. So, using calculus and your knowledge of tangents and normals, you can find the equations of the tangent and the normal at any point on the curve. And here they go. The tangent in red, the normal in blue. So that's the first exciting thing you can do with calculus. Find the equation of the tangent or the normal at any point on the curve you've been given the equation for. But it gets better. See, there are two special points on this particular curve which we often want to look at in more detail, or find out where they are on the curve, on the equation we've been given. Which 2 points do you think they might be here? They are the maximum and the minimum. There they are. Now, what's special about these 2 points as far as maths goes? Well, let me show you all the tangents again and watch carefully as they go through the maximum and the minimum. There is something important about the gradient of the tangent at both these points. You watch. Did you spot it? Here they are again. And what do you notice? Their gradients are 0. They have to be. This is true of every maximum and every minimum of every function. So, if we can find a way of working out when the gradient is 0, we will be able to find the maximum and the minimum points of the function we've been given. And this has a lot of important applications in optimization problems. Optimization just means finding the optimal value, which means the best value. And that will either be the maximum, if you want more of whatever it is you're graphing, such as profits, or it'll be the minimum if you want less of whatever it is you're graphing, such as costs. Okay, so guess how we're going to find where the gradient is 0. You've got it. We're going to differentiate the function to find its derivative, which means its gradient, and put that to 0. We solve that and we've found the maximum or the minimum. Again, you will do lots of these in class. Well, that's a quick introduction about how we're going to use calculus and how important it is. And by now you must be on the edge of your seats wanting to know how to actually do it. Well, for that you'll have to watch the next screencast. See you then.